first and foremost, I would like to say a few words. I can see many familiar faces, but this talk is geared for general public. So this talk is really aimed for people who do not necessarily have physics education beyond, let's say, high school. Okay, so but that does not mean that I'm going to dilute stuff, but it also does not mean that if you are going to, expect some stuffs that you see in your courseworks for the students of our department, you might be disappointed. So with that disclaimer, let us begin. So quantum mechanics, all of us have heard something similar to this, that nobody apparently understands it, yet everybody is somehow using it all the time. And the most famous example of such an adage is usually attributed quite rightly to the famous Nobel laureate physicist Richard Feynman, who in course of one of his lectures said something like this, that I think I can safely say that nobody understands quantum mechanics. And this is very frequently quoted. I'm sure all of you have seen some version of this in the internet. Now, what the internet and usually the science popularizations do not tell you is that these 3 dots in front of this quote is doing a lot of heavy lifting. They never share the full quote. And if you share the full quote, I really recommend that you go up and read the whole full quote. You will understand that actually Feynman did not try to say the most naive interpretation that you would make, that apparently nobody understood quantum mechanics. One evidence in favor of that, if you go to the Caltech archives, collected works of Feynman is stored in 93 boxes. Most of it is related to quantum mechanics. That's an awful lot of things to say about something about which he doesn't understand. So clearly he understood quantum mechanics, he taught students, and we also understand quantum mechanics. There are many things we don't understand, but there are many things we do. So today's lecture is about focusing about the things that we do understand. Okay? So with that in mind, what is this lecture about? So this year commemorates the 100th anniversary of quantum mechanics. And it's always very hard in science to mark that, okay, this is really the beginning of the phenomenon. It's not like that prior to 1925, nobody knew quantum theories or nobody had any inkling of what is happening. People, of course, were discovering many things experimentally. People were doing theoretical stuff. So the first ideas related to quantum theories goes back to 1900 to Planck. But Werner Heisenberg, the famous German physicist, wrote a 1925 paper somewhere in July, which we can correctly point out to be the start of the modern understanding of quantum mechanics. So usually that is created as a benchmark, and counting from that, this year would be the 100 years. And universe doesn't care about 100 years. We do as human beings. So we thought that we will celebrate it. So quantum phenomena and our understanding of them, they form the foundation of most, if not all, modern technologies. So quantum mechanics really pervades everything. It's not just a theoretical subject, it is really underlying all the technologies involving in the display screen, this laser pointer, the lights, the camera, everything. So given that, there is a usual mysticism that is associated with quantum mechanics, that nobody understands this is very difficult. On the other hand, if you look at the data, even high school students can understand the basics of quantum mechanics. Of course, not everything, but the basics, the rudiments can be taught. And this has been taught in the last 10 years or so. This has been done successfully in the globe. And maybe I will give you one concrete example at the end of this talk. So given this thing, I strongly believe that it is time to demystify this science and explain it not just with pretty pictures and metaphors, although I hope there will be some pictures and some metaphors, but also with examples and experiments. So we will try to really get to the nitty-gritty of the science, try to really understand it as much as we can, right? And given all the forewarnings about quantum mechanics, that is very hard, very complicated and all these things, you can very well say or guess that whether I'm being extremely brave or whether I'm being extremely stupid or perhaps both, well, I guess we will find out in an hour. Yeah? So with this, let's start. So first thing is that, as the great scientific minds of the Marvel Cinematic Universe told us, that quantum is supposed to be very small, right? Even Ant-Man, who can shrink down Even he needs to shrink down by several orders of magnitude before he enters the quantum realm and something like this. Well, sorry to say that this is a myth. It's a complete myth that only small particles like electrons or at most atoms and some few atoms like molecules will exhibit quantum properties. That's completely wrong. The modern understanding of quantum mechanics, which has been repeatedly verified in last 100 years, is telling us that nature is fundamentally quantum. Everything is quantum. You, me, this chair, the air in this room, everything is quantum. Okay? It's not that extremely small things are quantum and somehow when they get big, they start behaving in a completely different way. Laws of physics don't work like that. Everything is quantum. Nature is fundamentally quantum. There are very few rare phenomena for which we do not have absolute proof that they might have something to do with quantum, but even those we suspect strongly that they are manifestation of some quantum behavior. So what we call usually Newtonian or classical physics, like describing you and me, the physics that you learn in school, is understood to be an approximation of quantum mechanics. But it's a very good approximation. If you are someone who is dealing with everyday, day-to-day life physics, it's perfectly fine to not know or not use quantum mechanics and just directly use Newton's laws, and you will be fine. But it is still an approximation to quantum mechanics. So the correct picture is something like this, that quantum mechanics describes a huge swath of phenomenon, and on some corner of it, you can approximate this quantum mechanics by classical laws of physics. So this entire thing is subsumed by the laws of quantum mechanics, and unlike this picture, the boundary between these two regions is not very sharp. In fact, many interesting things happens between the boundaries, but I tried to make a sort of picture with all these blurry things and it was not looking in the slides good. So I decided to go for something which has a better contrast. Now, before we jump into quantum mechanics, let us very quickly recall Newtonian mechanics that we learned in school. Yeah. So consider a ball rolling down, or maybe a panda, because we have all seen videos like this. Now, to a very good approximation, this is described by Newton's laws. Yeah. So how does Newton's laws work? You have to measure the initial position and the initial velocity of the panda. So before it starts rolling at the top of the hill, figure out what is the top of the hill, what is the position, and figure out what is the velocity. Was it standing still or was it just already in a motion, so figure that out. Once you have figured that out, Newton's second law tells us that its acceleration is due to whatever force is causing it to roll forwards. In this case, it will be the gravity. And this second law actually allows us, starting from this initial information, to figure out what would be its velocity and position after some time instant. And then you can keep on bootstrapping this procedure and you can basically figure out what would be its position and velocity at any later time. So this is enough to completely determine the position and the velocity of the panda at any later time. And once you know these informations throughout the motion of the panda, the position and the velocity, that is really enough to determine any other physical quantities of interest to you. You can ask questions like how much energy did it have, how much momentum did it have, and any such thing. But everything gets determined once you know this initial data. So remember, once you know where the panda started and with what velocity, Newton's laws fix everything else. Yeah. But however, when we make use of this Newton's laws, we make some very simple, innocent assumptions. These assumptions are so innocuous that they are never discussed mostly in the, at least in the high school context. So it's a good idea to discuss them a bit. What are these assumptions? The first assumption is that we always assume that when we measure this initial position of the initial velocity of the panda, we do not really affect or disturb the physical system, the panda's thing itself. Seems like perfectly fine. The panda is sitting somewhere. I'm measuring its position. What's the big deal, right? We also assume that all physical properties can be measured to arbitrary accuracy. Of course, our present devices have some limitations, but 100 years down the line, we can measure it more and more accurately. And there is no limitation to this. We can build better and better technologies and we can measure more and more and more accurately. And in fact, you might even say that the physical property is same as the numerical value it takes. Like what is the mass of the panda? Whatever is the numerical value it takes when you put it on a scale. And finally, we also assume that the order of performing measurements has no bearing on the outcome. So I told you that you have to measure its initial position and velocity. You might say that which one should I measure first? Well, classical physics says that we don't care. You measure the position first, velocity later, or you do it the other way around. You get the same result. Now these assumptions, as we will see shortly, are actually too simplistic and too idealistic. And they get more pronounced when you really deal with something extremely small like an electron. But it's actually something that holds equally for any size objects. Okay? So enough about classical physics. This lecture is not supposed to be about 500 years of Newton's laws, but 100 years of quantum mechanics. So with that, let's start Quantum Mechanics 101 for very cool people. That's you guys. So think of the quantum mechanics as a game. Before we learn to play the game, we have to lay out the rules. Now I know the rules are the boring part. Nobody likes to listen to the rules, but it's important to have a nice, fair, competitive display of the game playing. So first let us review the rules. So what are the rules of the game? So first and foremost, we will restrict ourselves to the simplest quantum system because it's already targeted for general public. We don't want to discuss the most complicated system or even the mediocre systems. So let's talk about the simplest quantum system. And the simplest quantum system, the example is you can think of spin of an electron. So electrons have a property called spin. So it can be either completely up or it can be either completely down. So that's the example of a simple quantum system. So electron has many informations. It has mass, it has charge, it is moving around, it's zooming around. You ignore all of that and you just focus on one particular property of the spin of an electron. That is an example of the simplest quantum system. Another example, so this is something like this, that you have an electron. This picture I don't like, but then again, there is not a single picture that I like about the spin of an electron. So we have to be satisfied with it. So it can have something which is called spin up or it can be spin down. Another example is perhaps more familiar. You can think of polarization of light or photon. This could be left polarized or right polarized. All of you have, at some point seen some sunglasses or some sort of shades, and you have seen that comes, in polarized forms. So you can have something which is polarized in this direction or something is polarized in this direction, or in any other direction you can decompose into polarization of this and this. So these systems which can live in either of this or this is example of a simple or the simplest quantum system, and this is what we call a qubit, which is a short of a quantum bit. Okay? So throughout this lecture we are going to be working with qubits, right? Oh, I should have said at any point if you feel like you want to interrupt with some questions, comments, please feel free to do so. I want this to be as interactive as possible. Okay. So that's the simplest quantum system for which we are going to play the games. So what's the first rule? The first rule has to do with the question what. So what describes a given qubit? Somebody has given me a qubit, somebody has given me an electron. What should I use to describe that qubit? Now for an isolated qubit, so that imagine that you are in an ideal situation where in this whole universe there is nothing else except for that one qubit. For that isolated qubit, everything about it is captured by a single vector, and that vector is given the name a state vector. Sometimes it's also called a wave function. I don't like that name. State vector is more literal. It's a vector that tells about the state of the qubit, state vector, right? Now what is this state vector? Physicists like to denote these vectors in this particular symbol. It's just everywhere. If you are interested in quantum mechanics, there is no escaping this notation. So we are not going to sugarcoat it. I'm going to show you this notation. So this is the sign that this is a vector and the name of the vector is psi. And this vector lives in an abstract space. This is not a vector that lives in our ordinary space. It's not a vector that I can draw in this room or in this board or in this table. It lives on some sort of abstract space. Moreover, it gets worse. This vector is not something that you can measure. So you can ask all sorts of questions. What is this vector? Where is this vector? Who is this vector? None of those questions has any sensible answer. Okay? This vector is a completely abstract quantity. It's not something you can measure. It is not accessible through any experiments. In essence, you should think of the state vector as a really super abstract quantity, but you will see that other rules will allow us to extract the physical answers using this. Now, some of you might have a reaction at this point, which is like this, that he has given a weird vector in an abstract space. It's like a great way of describing something, but I mean, stick with me. So before we go on to the other rules, let me just defend my position a bit, that abstract spaces are perhaps not so abstract. You have already seen them, it's just that perhaps nobody has pointed it out to you. So first, abstract spaces are not just something that appears in quantum mechanics. They have already appeared, for example, in classical mechanics, in Newtonian physics. So remember Newtonian physics, I told you the state of any particle, any panda, is given by its initial position and velocity, which means that together they form a vector in a space which is not the ordinary space of just the positions. They form a vector in position of both position and velocity. So for example, let me show you a graph like this. So if you think of just Newtonian particles, here I plot the positions, here I plot the velocities. Imagine two particles completely identical, same mass, same everything, but one is in a given position at completely rest, so velocity is equal to 0, and another one is exactly in the same position, but it has some velocity. Now you imagine you apply a force to it. So imagine this pointer, it's completely static here, and I'm giving a force to it in the right direction. If it's completely static here, the moment I give force, it starts moving right. But if this same pointer at this same point was moving left, then I give a force, then first it will slow down while moving left, then it will start moving right. So it's a completely different motion, right? So even in classical physics, you are actually dealing with vectors in an abstract space, because the space which is both extending in velocity and position direction, who has seen that space? I have not, right? So, but we use them all the time. Another example is state of a gas, right? You know from high school physics and chemistry that a state of a gas is given by its pressure and volume. You can have some gas which has large volume but extremely low pressure, or some small volumes but extremely high pressure. And these are different states. And nobody ever bothered that the space of pressure and volume, that's a weird space. But it's still an abstract space. Who has seen the space of pressure and volume? I have not, right? So don't be scared by an abstract space where an abstract vector lives. In physics, you do it all the time. Now, let's go back to the first rule. Fine, let's accept that it is a vector. So what? Now remember, vectors can be added. And when you add them, you form a new vector. So for example, let me remind you, if you draw vectors as an arrow, if you have a blue vector and a red vector, and when you add them, so you just simply draw them tip to tip, and then you get this purple vector. And remember, the order of this addition doesn't matter. You can first take the red one and then you add the blue one to tip, you will get the same addition vector. Now, as in our high school, any vector addition is done much more simply if we choose a very nice set of axes, some good coordinate frame. So we will do the same for our qubit. Now, what can make a good choice of axis? Well, remember, I told you that spin has the property that when you measure it, it can be either up or it can be either down. So let's use this too as our axis, which means I can now draw the abstract space like this, that there is some x-axis which is now the spin up, or I can have the y-axis which is parameterizing the spin down, and an arbitrary qubit state is some vector along this line, and it has some part which corresponds to spin up and some part which corresponds to spin down, but in general it is somewhere both. So a general qubit state can exist in both of these states simultaneously, which is given a fancy name which is called quantum superposition. Superposition simply means the ability to add something and get the same thing back. You're doing this in quantum mechanics, so quantum superposition. And here A and B are just some two numbers, constants, like it could be 3, 4, 5, whatever you want. And we write this thing as a notation, as this psi is some A times in the 0 direction plus B in the 1 direction. Okay? Everyone with me so far? Okay.
Can I ask?
Yeah, sure.
Is there some sense like every 2 times of the zero state?
Yeah, there is some sense. You can just simply, do it, add it tip to tip. But we will soon see that it's better to think of these numbers as they will have some nice properties too. But I mean, yeah, in general, you can think of them as any numbers and you can just join them tip to tip. I will say one more thing without explanation, these numbers can even be complex. So it's perfectly fine to have that. Okay, so second rule. The second rule has to deal with the question how. So how does this state relate to experiment? We have an abstract vector living in an abstract space. Fine. At the end of the day, we want to do experiments. And I need to know how does this state or the knowledge of this state help me in trying to predict the outcomes of any experiment. So remember the state, a general qubit state we wrote like this. Now if we measure its spin, our detectors are incapable of detecting some superposition. They will never do that. If you measure the spin of any qubit, its detector will always give you the reading that either it's spinning up or it's spinning down. You will not get something like spin up and down. Detectors don't detect vectors. Detectors will detect some number. So they will either give me back the answer that up, or they will give me either the answer back if the spin is up pointing down. But then the point is that if it is really in some general direction, which one will we see? Will we see up or will we see down? If it was just 0, we know that we will always see it up. If it was just 1, we know it will always see down. But if it is both, quantum mechanics tells us that sometimes you will see up, sometimes you will see down. You will never be able to predict which will come out in a given experiment. But what you can predict is the relative probabilities. How many times, if you do this experiment a large number of times, how many times will it point up and how many times it will point down. And these probabilities are given by the number that if you want to get up, you take the number in front of it and you just square it. This vertical sign simply means that you should take its absolute value. Okay, so in case you can even have negative numbers here, you should take its positive thing. And the probability of seeing down is this b, and you just square it, and that's it. And now, does anyone want to guess that what is the relation between this a and b given this interpretation? Anyone, preferably from non-physics background? So think about probabilities. What does probability says, right? It says that either this can happen or that can happen or that can happen, etc., right? I'm saying that here in this experiment, there are only 2 possible outcomes. Either it will point up or it will point down. The chances of it pointing up is mod a squared. Chances of it pointing down is b squared. So it has to either point up or it has to point down, which means that if you add them together, you should get 100% of the probability. So these 2 should add up to 1. Okay, so that's why when you said it's 2, I said that maybe 2 is not a good number because it's already greater than 1. Okay, so this probability is the only thing we know for sure. We do not know the outcome. Now probabilities are nothing new to us. All of us are familiar with probabilities or chances. Life is uncertain and so on and so forth. But there is something fundamentally different about this probability and the probability that we usually discuss in our everyday life. So let's take a very common example, coin toss, right? Coin toss is also something which has only 2 outcomes. It will either flip on head or it will come up with the side which is tails. And if it's a fair coin, we say that it's a 50-50 chance. It will either be head or it will be tail. Now really think about it. Why is it that a coin toss gives you probability? If coin is a classical particle, why can't I just simply use Newton's laws to predict? So if I really measure very precisely that where the coin is, how much force am I imparting, what is the initial direction, I should be able to calculate the whole revolutions and the whole trajectory, and I will be able to figure out what side will come up. The only point is that this is a very complicated computations. There are so many variables. There could be air flowing in the room. The coin might not be a perfect one. The force imparted by a person might not be so uniform time to time again. So there are a lot of factors that you need to know about. And most of the time we say that, fine, let's ignore those factors. Probability in a coin toss is a consequence of our ignoring those factors. If we had kept track of those factors, there was no probability. You would be able to predict with 100% certainty every time whether it will come out to be head or whether it will come out to be tails. So in classical world, when we say that there is a probability, it is actually quantifying our ignorance. It is basically saying that we chose to ignore some information and there is a price to pay for that. In quantum mechanics, that is not the case. To the best of our knowledge, nature is fundamentally quantum mechanical, probabilistic. Okay? It doesn't have any hidden information that if you knew, you could predict with certainty. No. So this is a very important and crucial difference between quantum probabilities and classical probabilities. Okay, so we have this result, and once we have that, immediately after our measurement, the quantum state, the qubit, will jump to the corresponding state. So for example, if we detected spin up, it will jump to the state 0. So initially this qubit was in some state like this. We did a measurement and we got, the detector said it's 0, of course with some probabilities. But immediately once the detector said it's 0, we know that immediately after maths, the state has just been completely along the 0 direction and it's precisely psi is 0. Okay? So if you do a measurement, you get 0, and you do immediately another measurement after that, you will get 0 again with 100% certainty. Okay? That's the only time in quantum mechanics life is not uncertain. Okay. So this, sorry, was there a question? No. Okay. So this quantum superposition is actually behind the famous or the infamous Schrödinger's cat. All of you have seen this experiment which Erwin Schrödinger proposed, where a cat is put in a box with some sort of radioactive vial which is activated or deactivated depending on whether some quantum process happens or not. And if this vial gets broken, it releases a poisonous gas and the cat is dead. And then the whole question is that somehow the cat is in a superposition state of both alive and dead. And until you really open the box, until you really do a measurement, you are not going to see the cat is in a alive state or a dead state either. And this is the usual story that goes on. And it's a very weird, strange, unfamiliar story, but yet this is extremely true. It's our nature, in our nature, there are fundamental particles, fundamental systems which are continuously being put into situations like this, and they exhibit exactly behaviors like this. I don't know of cats, but particles definitely behave like this. And if you want, we can do one experiment like this right now. But it's up to you. There is not enough enthusiasm in this room to do this experiment. So yeah, okay, now it's better. Okay, so the way to do this experiment, and in fact way to do most quantum experiments right now, has become extremely easy. It's via using access to any of the publicly available quantum computers. So we will do that one right now. So this page shows the IBM quantum composer. So IBM has an array of quantum computers that public can access. You need to create an account. It used to be free, but until few months ago, now everyone gets up till 10 minutes per month free. After that, it's not, and it's quite costly. So use your 10 minutes well. But well, this one will not take only seconds. So when you open this quantum composers, you get something like this. You get Q0, which is basically a single qubit, and you get a C1, which is a classical bit. So why do you need a quantum bit and a classical bit both? Well, quantum bit is the one on which we will do some quantum operations. But at the end of the day, I'm going to do a measurement. An outcome of a measurement is always going to be some number. And that number is going to get stored in this classical bit. Okay? So if you want to create a superposition, on the left-hand side, you see this huge array of blocks. These are the different operations that you can do on a quantum bit. Okay? So one of the simplest way of creating superpositions with exactly 50-50 is done by this gate, which is called a Hadamard gate. So you just simply drag this and release this, And you can immediately see here that the histogram changed from completely on 0 state to equally in 0 and 1. This is not the outcome of an experiment. This is the theoretical prediction. Okay. Once you have done that, there is nothing else. We have created a superposition, right? Now we need to measure it because we cannot detect a superposition. A quantum of measurement will always detect either it's in up or it's in down. So how can we detect a superposition? If we do it once, is it enough? No, right? Because if we do it once, it will come out up or down. How do I know it was in a superposition? It could have been in an up or it could have been in down. So I have to repeat this experiment a large number of times and look how many times I get up, how many times I get down. If the number, is relatively 50-50, then I have a very good idea that this theoretical modeling was correct. So to measure it, you have to come to this block, which looks like a meter. And if you hover over it, it says that what it is. And you drop it, and it will measure. And you can see that there is a small arrow that dropped to this. So it says that I will measure, and whatever outcome I get, I will store in this EBIT. And now it is essentially ready. Now you have to do an extremely complicated step, which you have to follow very closely. You just come onto the top right and click setup and run. Once you do here, you will get a lot of these options. So you will see the current available quantum computers that are to you. So there are 3 that are available. So one which has 23,000 pending jobs, probably not the best idea to submit our job there. The other 2 has 0, so we can select any of them. So let's select, let's say IBM Torino. And here there is something called shots. Shots means how many times you want this experiment to be repeated. Okay, so 1024 is a good enough number. Once you have done this thing, so we will say run circuit, and it will start doing this. We can go to the job page, and you can see it will take some time. Let's say, I don't know how much, like hopefully not too long, but usually should be done in, let's say, 20-30 seconds. Sometimes it helps to just refresh the page. Yeah, so it's completed, and this is the outcome. So if we come here, we see that it gave 0 530 times, and it gave 1 494 times. What was the expectation? Remember, we did 1024 times, so it should have been 512 ideally. But we got 494 and 530. So does this mean quantum mechanics is wrong? Yes, no? Almost right? So speak out loud. Why do you think is this discrepancy there? Why isn't like exactly 512, 512?
We need infinite measurements.
Yeah, so probabilities are something that is interpreted like, 50% means if you repeat it infinite number of times, then you get half. Like even for coin toss, right? It's supposed to be head and tails, but if you have ever tossed a coin, you know that you don't get alternating head and tails, right? So you get all sorts of patterns. You can get 5 heads in a row even. So that's that. There is another factor, which is that the quantum computers that we have at our disposal, and definitely the ones that you can run on a free account, are what are called noisy intermediate scale quantum computers. These ones are not completely perfect. Okay, so there is some small hardware fluctuations for which there are small errors that creep in. These errors can usually be corrected, but in this very simple example, we didn't do that. So it could also be because of that. Okay, so the number of the fact that you need to repeat it infinite times to get this, you can improve it by increasing the number of shots. You run it 10,000 times, run it 20,000 times. But the other one, you have to correct it in a different way to an extent. But then hardware limitations will always tell you that, okay, fine, beyond this, you cannot improve your accuracy right now. But given this is a pretty good outcome. Quantum mechanics is not in trouble, and we have created superposition successfully and measured it live. Okay, this actually went and ran into a quantum computer and created this thing, and then it happened 50-50. Okay, so let's come back to the rules. Third rule, what about other quantities that we can measure, right? you can have all other different quantities, energy, momentum, so on and so forth. You might not be just interested in spin, although for just the simplest quantum system, qubit, spin is really the only thing that you can measure. But in general, you can think that if you have an electron, you can measure other properties, right? And these are now captured by something called operators. And at this point, it's a valid reaction that you might say that, okay, I mean, this is getting out of hand. What is this operator? Operators are just a fancy name for saying that these are some ways of transforming one vector into a different vector. That's it. That's the job of an operator. Okay. So an operator A hat, what it does is that it takes an initial state vector which is pointing along this, and it will just simply rotate it maybe to this direction. That's what an operator does. Okay. As simple as that. One important thing about operators is that unlike numbers, the multiplication of operators do depend on the order. So for example, if I have operator corresponding to position and momentum, then if I first transform the vector by acting the position operator and then the momentum operator, and if I do it the other way around, these two will not lead to the same final vector. And this statement is actually at the heart of the uncertainty principle. So the uncertainty principle is in fact something that is derivable starting from this rule. Okay. So we have the third rule which says that if you are interested in other properties, just find the correct operator for that, and that operator will tell you that how to take it to the different vector, and then in this different vector you do your measurement. Okay. So we will not make use of this third rule a lot, but just for completeness it should be there. We will make even more or less use of the fourth rule, which says what if you do not measure anything? Who told me that I have to measure this? Who told me I have to measure this right away, right? What if we don't measure anything? What happens to the state vector? Does it remain just pointing along this one direction, or does it start changing? Well, it doesn't remain static. It changes, it evolves with time, and the way it evolves with time is dictated by the operator corresponding to the total energy that the system has. Okay. And this equation, don't worry about this equation, we will not deal with it, but this equation is the famous Schrodinger's equation, which is the 99th, this is the 99th year of that. And this equation simply says that so H is the operator for the total energy of the system. That tells me that how should it evolve with time. Okay. But we will not make use of this, but just for completeness it should be there. And this was the final rule. But before we proceed, there is one further setup that we should describe. So far we have been talking about a single qubit. What would happen if we have two qubits? So if we have two qubits, there are something new things that you can do. There are some new phenomena that comes out. So that's why double the fun. So if you have two qubits, you have many more possibilities now. You can have the first qubit which is spinning up, or you can have the second qubit which is also spinning up. We will represent this state by 0, 0. You can have the situation where the first one is spinning up but the second one is spinning down. You will call this 0, 1. You can have the situation where the first one is spinning down but the second one is spinning up. We will call this 1, 0. And finally, you can have the situation where both are spinning down. So we will call this 1, 1. So there are more possible states in which two qubits can be. So they can be together in a total of 4 different states. And in general, it tells me that a 2 qubit state can therefore look like some number in this plus some number in this plus some number in this plus some number in this. And I cannot draw a picture for this because it's not possible yet to draw a 4-dimensional space. So, sorry, was there a question? Okay, no. So why is this fun? Because now you can actually do many kinds of experiments. We can do 2 distinct measurements, one on each qubit. And when you do that, sometimes something very funny happens. So suppose let's look at the case when A and D is equal to 0. So remember the general qubit in 2 qubit state was like this. So let's look at the special case when this number is 0, so this state is not there, and this number is 0, so this state is not there. So we have just the middle two. So we have some number times 0, 1 plus some different number times 1, 0. Now if you measure only the first qubit, So you just measure the spin of the first qubit. You see something funny happens, that just measuring the first qubits, its outcome automatically tells us the state of the second qubit without us doing an experiment on the second qubit whatsoever. Why does this happen? Because this 2 qubit is in a state which is, when this one is spinning up, the second one is spinning down, or when this one is spinning down, this one is spinning up. When I do an experiment on the first qubit, I'm going to get the result either it's spinning up, in which case the other one has to spin down, or it's spinning down, in which case the second one has to spin up. So somehow, by doing experiment on one of the qubits only and not touching the second one at all, we have figured out what the second qubit state is. When this sort of thing happens, and of course you see this is very special, this only happened because we set A and B equals to 0. This will not happen all the time. So not all 2 qubit states are going to behave like this. Some 2 qubit states are going to behave like this. Those 2 qubit states are special enough that they are given a name. We call them, they are entangled. They are somehow, completely entwined with each other. So doing something to the one has some effect on the other. And the funny thing is that this entanglement persists irrespective of the spatial location difference between the 2 qubits. In principle, this could be very, very far away, and this phenomena would still be true. So this is the fun bit about the 2 qubits, and this is really all that I have to say about the rules. With this done, just one final summary slide, that what happens when you have quantum mechanics in action. You have some system in some state, you try to measure it, you try to observe it, take a picture of it. You don't know a priori whether you will get spin up or spin down in one single experiment, but you can predict the probability that you will get probability of 0 by a square, probability of getting 1 by b squared. So suppose you take a picture and you say that you got up or 0 state, the probability of detecting which was a squared. Immediately after that, the system will collapse into the 0 state. Okay, so this is really one slide summary of how quantum mechanics works, as long as it's for a single qubit. So that's the rule, that's the setup. We are ready to play the games. Okay. So if there is any question about the rules, this is a good place to ask. I'm not saying that you cannot ask later, but this is a natural place to ask. If not, we move on. Okay, so let's move on. The first game or the first experiment we do is an impossible experiment. Why is it an impossible experiment? Well, there is a rocket that has been made. Don't ask me where or who. Someone has made it. And this rocket is activated whenever a photon is absorbed by it. So you send a photon towards it and it absorbs it, and immediately it is activated, it starts flying off and goes into some direction. The rumor is that there are some defective rockets. Our job is to find out, given a set of rockets, which ones are defective and which ones are functional. How do we find them out? Well, we can shine a light. If it is a good rocket, then it will fly off. And if it is a defective one, then the light will just simply pass through unaffected. It will not fly off at all, and we know for sure it is defective. Right? It's a simple enough test. There is one catch. If you do this experiment, you will have no more good rockets left. All good rockets have flown off. Now, if you are a physicist, you might be happy with this. If you are a businessman, perhaps this is the worst idea ever. So what do we do? If you think about it classically, it is impossible to test these rockets without exhausting our supply of good ones. It's impossible. What can you do? If you test them, they fly off. If you don't test them, you don't know, right? So this is reminder of the old adage, right? That you cannot have your cake and eat it too. You have to choose, right? You can either say that, okay, I have a cake, or you can say that I ate a cake. You can't have both. It turns out that this has a solution if you use quantum mechanics. And the solution is given by these two gentlemen, Elitzur and Weidmann. And in their paper, for reasons completely unknown to me, instead of rockets, they discussed a bomb. So just for attributions, let's now imagine that this rocket is a bomb, which instead of flying off will explode. So hopefully not too violently, but nevertheless, and we want to find out the good bombs from the bad ones. So the way you do it is that you set up an experiment like this. Let me describe this experiment. There is a light source. This light source comes in, and this is something called a beam splitter. So this beam splitter's job is really to put this single photon into a superposition state. So it can, at this, after hitting this, it has a 50% chance of going up or a 50% chance of going in this direction. On one of the path, we don't put anything anymore. There is a mirror. It reflects everything back faithfully 100%, and it enters another beam splitter. On this other path, we put the bomb that we wanted to test. Okay. Now, two things can happen. One scenario is that if you do not have the bomb, imagine for a moment that this bomb is not there. This setup is actually something which is 130 years old. It's called a Mach-Zehnder interferometer. It was an experiment done in 1890s. And what happens is that if you have these two exact same beam splitter, this light and this light will combine in such a way that all of them will just go into the detector 1 and none of them will go into detector 2. Okay? So if there were no bombs, if this was just a completely transparent thing, these two lights, even though they are split here and even though they are split here, this two splitting works in such a way that all of the input light comes out and gets detected in the detector 1. Okay, that's one thing that you need to know. Now, with the bomb, there is something amazing that happens. Why? So this is once again the setup. So let us consider the two scenarios. The first scenario is the bomb is a dud. It is a defective bomb. Okay. If it is a defective bomb, then the situation is exactly the same as the Mach-Zehnder interferometer, where there is nothing here, because the light just simply passes through it. The bomb doesn't interact with it. It doesn't absorb it. It doesn't do anything. So we will see all the lights come out in detector 1. On detector 2, we will not register any light at all. Okay. So this is the boring scenario. Nobody likes this scenario. The second scenario is the exciting one, or the dangerous one, depending on your perspective. So suppose the bomb is live. Then what can happen? So now we have three possibilities. The first possibility is that the photon went along the bomb's path and indeed it absorbed it and it exploded. And at this point, you already see that we run into the problem that quantum mechanics, or anyone who has studied quantum mechanics, knows for very well. It is very difficult to describe quantum mechanics using human English language, because the photon is really not going along in one of the paths. It's in a superposition state. It's in this and it's this. And the bomb, when it's a live bomb, it is actually acting like a detector. It's trying to detect whether the photon came this way or not. So this detector, if the photon came this way, and 50% of the chance when the photon will come this way, this detector will register a photon, and in that case, the bomb will explode. So it's not really that the photon went along that way. 50% of the time, there's a probability that the bomb will be detecting the photon going along that way. But for language issues, we have to say something like this. So this will happen 50% of the time, because as I said, this beam splitter splits this in a 50% superposition of going up or going this. So it will have 50% chance of being detected in the safe path or 50% chance of being detected here. But and when this happens, of course, the bomb is exploded, your detectors are all gone. Even without the detectors, you know what is the outcome of the experiment. You're probably dead. So you know what is the outcome of this. The other situation is that the photon gets detected at detector 1. How can that happen? It can happen because, remember, the 50% chance it gets detected in the safe path, 50% on this. So when it went along really the safe path and it came here, it will not get any more contribution from the green path, because the bomb did not explode. We know that the photon for sure has taken this safe path, and here now it will get splitted like this, and there is half of the chance that it will go here, half of the chance it will go here. So half of the time it will go and end up at detector 1, and the other half of the time it will go and end up in detector 2. So even when the photon actually took the safe path, it somehow knew that there is a live bomb sitting on the other path. There's a potential of getting detected. And this is something that is very crucial, because now if you are an experimentalist and you do not know the details of the theory and you are just working at an operational level, then you will simply ask the question that what detection means what. And you see, of course, there is this thing where everything explodes. So that's not a good thing. If you see the detector 1 is detecting a photon, you do not know whether it's because of this scenario or whether it's the case 2 of scenario 2. It could be because the bomb was a dud and the photon just simply went along and got detected at detector 1. Or the bomb was alive, but it still had some chance to get detected at detector 1, so that's what happened. But every time the photon gets detected at detector 2, you know for sure that the bomb was a live one, because that's the only way the photon can get detected at detector 2. So every time you have detector 2 detecting a photon, you know for sure that this bomb is a good one and it did not explode.
Yeah, I mean, I understand copy your points, but my question was about the beam splitter. Can you repeat the function of that?
Yeah, so the beam splitter puts this photon in a superposition state. So imagine that this photon is coming in the 0 state and it puts it into 50% 0 plus 50% 1 state. So so imagine the upper path as the 0 state and the lower path as the 1 state if you want. So it puts it in a superposition. Okay?
So instead of splitting the beam, it rather navigates it to one or the other direction, but we don't know which one.
Yeah, so in fact that question doesn't make sense until you do a measurement. Remember I told you that if it's in a superposition, you cannot say that whether it's in up state or down state. You can do a measurement and then you can say something that, okay, fine, yeah, that this one was in upstate or it turned out to be in upstate this time, something like this. So the bomb is actually doing the job of the measurement, but then the point is that because it's trying to measure it, this path is sort of getting blocked off because there is a measurement device that is sitting there. And so what is happening is that only this path is sort of playing the role. And you remember in the original Mach-Zehnder interferometer, the fact that everything got detected at detector 1 crucially dependent on both the beams recombined at this beam splitter. So if this one is cut off, then this one just simply gets split again. And so there is a 25% chance. So 50% chance it takes this path and then 50% of 50%. So that's 25% chance it will go here or 25% chance it will go here. But when it is going here, we know for sure it happened because this path got blocked off. And the only way that path could have been blocked off is because the bomb was a live one. If the bomb was not a live one, then that path was not going to be blocked off. It's going to let the photon paths through. Okay? Yeah.
You said when there is no bomb or no rocket, then the light always ends up in the detector 1. Is that the property of the beam splitter?
It's property of the whole setup.
Oh, okay.
Yeah.
Is it important to understand this property or?
It is of course important for this whole setup, but I mean you can take it as a given. Like I mean, suppose you have a setup like this, then this works. Yeah, please.
Yeah, my question was exactly related with that. And I in the case that there is no bomb, always will go to the detector 1. You mentioned that you just given this.
Yeah. So you remember this one creates a 50% chance of superposition. Then this one actually once again combines them in such a way that it recombines everything and just puts it like this.
Why? Because you mentioned that these beam splits are just, that's how you push. See from there. Sorry, mine just not that.
No, that's fine. Yeah.
So you just give this, right?
Mm-hmm.
You just assume everything.
Mm-hmm.
Okay.
No, I mean I don't have to give you this. I can show you the equations, but I was trying to avoid that in the public lecture. So the idea is like this. So suppose you have this and you split it like 0 plus 1 and then it comes here. Then this one acts like this, that when it takes this and it takes this, it goes back to 0 again. So it just adds a 0 minus 1 to it in some sense.
So like the beam splitter is the operator, and like if I apply
Yes.
both operators, I
Yes.
get the same
Exactly.
state.
Exactly.
But
So
if
these
I
beams,
put something in between those two applied,
exactly. That's the thing. So this beam splitter is an operator. This is another operator, and they have the property that when you take two of them just back to back, that's like doing nothing. So the original state goes to the original state. But if you put a measurement device in between them, then everything changes. It's a completely different ballgame. So because of quantum mechanics, we have a 25% chance of detecting something which was previously completely impossible. Okay. So once again, this is something that we can test in a quantum computer once again. So if you want, we can test it, or if you don't want, we can just move on.
sure.
Okay. So unfortunately, this one is not going to be through the circuit because when you get more and more complicated, it's easier to write code. So, but hopefully the end result would be fine. Okay. So we have a quantum bomb tester, and we have an option. We can insert the live bomb, or we can insert a dud, right? So I'm pretty sure nobody's interested in inserting a dud, so let's skip that. So we insert a live bomb, and you see that the outcome of this. So let me just sort of tell what is the different things. So the way I have parameterized it is that the 0, 1 represents a success. By success, I mean that these are the bombs which have not exploded and which we know for sure is being live. Okay, so this is the case which is corresponding to being detected at D2. The explosions are the case where you have this. That's the 50% roughly case, and uncertain is the case which is here because it has been detected at D1, right? And you see that roughly you are supposed to get 25%, 25%, 25%, 25%, and we repeated it 10,000 times. And we don't get exactly 2,500, but pretty close to it. Once again, this is because of the combination of the two factors that I said, that the fact that you are doing this 10,000 times, not infinite times, and there are some limitations to the quantum hardware as well. But it's pretty close to 2,500. Okay. Yeah.
This 25% is when you have the bomb and actually it broke.
Yeah, I mean, and it did not explode. Yeah, I mean, it did not explode because if it exploded, then I've lost the bomb, right? That's like the original scenario. I mean, so I want the scenario where I know for sure this bomb is a good one, but it did not explode. So that's the second column. Okay. Okay. So I mean, we can insert it once more, see if it improves. Okay, this time it got a little better. So that's that.
I have a question.
Yeah.
When you set up the experiment that the detector 1 and detector 2 exchange their roles, or
Sorry, can I set up or did I set up?
if you can set up the experiment somehow, like modulate the phase of the beam that the detectors.
Sure. Yeah, I mean, you can do many more things. This is the simplest realization of this. Yeah. Okay. In fact, while we are discussing modifications of it, let's go to something important, which is what I call Mission Impossible N, in lieu of the fact that this franchise is popping out movies one after the other. And so we have achieved the impossible and we want more. We want to ask, can we somehow improve the success rate above 25%? And it turns out that we can. You have to make use of quantum Zeno effect, or what is also called a watched pot effect. So Zeno of Ilia, I hope all of you know the story, that he was a Greek philosopher in 500 BC who saw an arrow flying and interpreted it as that motion is impossible because at any given instant the arrow is sort of fixed. So if at any given instant it is fixed, then how could it be moving at all? So Zeno of Ilia is someone who saw motion and concluded that motion is completely impossible. That seems like a very bad physics thing to do. Unfortunately, the physics effect that is named after him is very real physics effect. And that physics effect is related to the thing that I already told you. Remember that if you take a qubit and you measure its spin, and suppose it collapses to state 0, And then if you keep on measuring it immediately afterwards, you're going to force it to stay on state 0. It will never get the chance to evolve to something else. Because if it's 0, then it's 0 with 100% chance, and then it will keep on staying there. So if you have a state, you watch it once, it collapses to state 0, and you keep watching it, it will never get the chance to go and rotate and explore the other parts. It will keep on staying there. So every time it tries to evolve, you watch it again, it collapses back to this. So this is called quantum Zeno effect, or a watched pot effect, named after the fact that anyone who has tried to make a soup, every time you want to see it boil, it never boils, and you go to that other room and it starts boiling all of a sudden. So how do we make use of this? So we put the bomb now in what is called an optical cavity and separated by a beam splitter. What is that setup? That setup looks something like this. It's a hollow thing where there is a very tiny insertion through which we send in the photon. And this whole hollow cavity is cleanly separated into a left region and a right region by a beam splitter. Okay? The bomb is always in the right cavity, the photon always enters through the left cavity and moves towards the beam splitter. That's the initial condition. This beam splitter is now a new one. This beam splitter has extremely high reflectivity. So the photon almost always bounces back in the safe side. So when it hits this beam splitter, most of the time the probability is that it will stay in the left one. Very tiny probability is that it will leak on this side and it will encounter the bomb. And if the bomb is alive, it will explode. So the state is written something like this. If you are familiar with these functions, it's good. If you are not, ignore it. So this is just simply saying that the 0 is the left state, 1 is the right state, and there is a very high chance that it should go to the left state and very low chance that it will leak onto the right state. Once you have that, this cavity has the property that every time the photon bounces back and hits the wall and comes back to this again, it rotates very slightly. It rotates precisely by pi over n, where this n is the same n that appears here. So the photon comes here, hits here, goes back, and then goes back again, and then this time it rotates back very slightly. Now the effect of this slight rotation is that if you do it n cycle of time, it will eventually try to leak off to the other side. Because after n cycles, this rotations, this sign will now become pi over 2. So this becomes 1, this becomes 0. So there is 100% probability that it will go over to the right side. But it's only because if this bomb is dud, so there is nothing to detect the photon on the right side. So you repeat this experiment n cycle of times, you let the photon bounce around n times, right? You choose n, right? 10, 100, 1000, as much time as you have. Eventually, after this time, you measure the photon, and if you see that it has come out on the right side, you know that the bomb is a dud with certainty. On the other hand, if the bomb is not dud, it's live, the situation is different. This bomb is continuously detecting the photon state on the right side. So it's every time it's trying to bounce through and leak through, this side of the photon is, we know for sure that if the bomb has not exploded, the photon has been in the left side. So this bomb is actually doing the quantum Zeno experiment. It is continuously watching the photon. And because it is doing that, it keeps on collapsing the photon to the left side, and a very tiny probability exists that it will appear on the right even after n cycles. So after n cycles, if we see the photon is on the left side, we know for sure the bomb is a good one. If the photon is on the right side, we know for sure that the bomb is a dud. There are very few fraction of chances in between these two possibilities where the photon is going to leak onto the right side and the bomb is a good one and it will explode. So we can actually, using this, improve our detection of successful good bombs to an arbitrarily high number, as close to 100% as we like. So once again, we can do a short experiment to see this. Okay, so here we have, once again, I'm pretty sure nobody wants to insert a dart bomb. So this one is the classic one, which is also called the single shot. So let's change over to the quantum Zeno, and let's take the minimum possible number, so 2. So if you just run it 2 times, The green one is now the successful thing, and you see that how much it has jumped up by. So it has already improved the efficiency by a lot. And now if you keep on changing, so if I go to somewhere around 10, it has already jumped up to 95. And then if I increase it even further, it goes up to 97, and very soon it reaches as close to 100% as you like. Okay? So what was classically absolutely impossible, in quantum mechanics, not only is it possible, it's something that is extremely efficient. Now, okay, for bombs, you might say that even 1% probability that it will explode is a bad thing, but that's why I said that I don't know why they chose it to be bomb. For any other things, it's a very good success rate.
Can I ask you a question?
Yes.
Because this result seems to me unlogic, because with increasing n, n means the attempt to go from left to right.
N means how many times I let the photon bounce through.
Okay.
So n is this one, this n.
And it doesn't mean how many times it hit the beam splitter.
I mean, yeah, you can think of it like how many times it hit the beam splitter as well. Yeah.
I hit it more times, and there is lower chance that the bomb will explode.
Yeah. That's
Doesn't
because
seem very logic to me.
that's because this beam splitter is the very special one, which has a very high reflectivity of putting it on the left side and very low transmittivity to put it on the right side. It's because of this extremely special beam splitter. If we use the previous beam splitter, this experiment is not going to work. You need a beam splitter which has extremely high reflectivity and extremely low transmittivity. And by the way, this is, of course, we are doing it in quantum computers, but this is an actual experiment that has been done in 93, 94. Yeah.
So what would a material or a device be that has this characteristic of it being highly reflective?
I mean, a very good mirror, for example.
Okay. Okay.
Right? So something which has an extremely high reflectivity, low transmittivity is basically a very good mirror. Yes.
Just a quick question about their software that they are using.
Yeah.
Because I suppose there isn't you don't have a bump out under the node. So, and I suppose also using some Python random package would not be really.
Yeah. So this what I'm using is Qiskit. That's the software development kit that IBM has put out. That's by far the most popular and user-friendly one to run quantum computers and so on.
Okay. Yeah.
It's open source. The full documentation is there. I strongly recommend, if you're interested, check it out.
Thanks.
Yeah. Okay. So moving on. We are doing quite badly on time, Vashik. So I mean, please interrupt if you say that you're bored and you want to leave or something. So the second one is quantum teleportation. So classically, if you want to share a physical information, you basically need to carry the object somehow from the sender to receiver, right? If I say that I want to give you this pointer, I want to share this pointer, there is no way for me to share this pointer other than just simply throw it to you or walk and give it to you. But quantum mechanically, you see, two qubits are completely identical. So even without exchanging qubits, if we can somehow exchange the state my qubit is in to your qubit, that is essentially functionally me sending across the qubit to you. So the whole question is that can we do this in quantum mechanics? And the answer is yes, we can. This is called quantum teleportation. And the reason I call this exposed is because this is something you see in sci-fi movies like in Star Trek or other series all the time. The breaking news is that you cannot use this to send information instantly or faster than the speed of light. I mean, I'm sorry to say. And we can explain this, how it works. And because we are going to explain it, perhaps a better title for this slide should be that quantum teleportation explained, not exposed. Okay? So how do we explain it? So we explain it using a protocol that I'm showing here. There are a lot of things going on in this picture, so let me break down one by one. So there we have two characters, Alice and Bob. They are extremely happy because they live in a world where they have plenty of grants available for them to do as many quantum experiments as they want. So they went to a local entangled pair production machine, which if you ask them nicely, they give you an entangled pair. So this entangled pair production machine has given them a pair of qubits which are entangled. Alice has kept one, which is A. Bob has kept the other, which is B. This company also sells them two devices, one for the sender, the other for the receiver. So Alice is the sender and Bob is the receiver. Alice has a different qubit T whose state she wants to send to Bob. And the idea is that the state of this qubit T, which is the qubit that should be transmitted, somehow this state should come and appear in the state of the qubit P. Okay, so T is the qubit that will be teleported, and A and B are the original entangled pair. So how does this protocol work? The protocol works in this way. Alice takes her two qubits, one part of the entangled pair, and the second one is the one which she wants to, whose state she wants to send, and she performs a very specific experiment, a measurement on them, which is called a Bell measurement. Okay, it's a very specific measurement that you can do only on a pair of qubits. So remember when I said that you have a pair of qubits, you can do many kinds of different things. You can measure them individually, you can measure one, not measure the other. You can do a measurement on both of them in a very specific way, which is called a Bell measurement. When you do that, you can get 4 possible outcomes. So corresponding to that, her device is going to light up either because the possibility 0 has come, or possibility 1 has come, possibility 2 has come, and possibility 3 has come. Okay, there is equal chance of any of this thing happening. So 25% chance 0 will appear, 25% this will appear, then etc. It doesn't matter which appears. Whichever one appears, Alice is then going to communicate this to Bob through a classical channel. So she is going to send a text message that, you know, I got X. So X could be 0 or 1 or 2 or 3. Corresponding to that, based on that text message, Bob in his machine, he has available of 4 operators with which he can act on his qubit. So if Alice says that she got 0, Bob will choose to act the operator 0 on this. If Alice says she got 1, Bob will choose the operator corresponding to 1 on this, and so on and so forth. And now the claim, without showing the math, is that there is a set of such sending and receiving machine with which this works in such a way that when you do this protocol, the state in T will just reappear completely and instantaneously on B. Now, can anyone explain that why this does not allow faster than speed of light communication? Because, you know, it seems like the moment Bob will do a measurement, the state on T will just instantly appear on B. Any guesses?
Because of the first normal message.
Yeah, so because of the fact that this protocol crucially dependent on the fact that Alice has to send a normal message to Bob. And that is limited by the speed of light. You cannot send SMS faster than the speed of light. I mean, we cannot send it close to the speed of light anyway. So that's the thing. The whole teleportation protocol, and this is something that you can try to do whatever you want. You can say that I will come up with an even fancier protocol, more complicated, more nuanced math. There is nothing that you will be able to do unless there is one classical communication that has happened. Okay, but this is still quite impressive because you see the state of this qubit can be instantaneously transferred into this. The time is not important, but the space is important, that Alice never needed to remove this qubit and get it over to Bob. So Alice could be sitting in Los Angeles, Bob could be sitting in Mount Everest, and this will still work instantaneously without them taking the qubit all the way and going over it. And that's quite impressive. So this is, of course, another experiment that we can do, unless all of you are bored. Okay, people are bored. Someone is nodding. So okay. So in this one, essentially what is going to happen is that we are allowed to fix our initial state, like the state that Alice's qubit is in, which she wants to state. right? Which she wants to send. And we can adjust this slider to make it whatever proportion of probabilities of 0 and 1 we want it to be. And whatever it is, once we send over this data, we are going to see a comparison. Like we are going to do a final measurement on Bob's side, and we are going to compare it with the original one that we intended to send and see how much we agreed, right? Of course, theoretically it should be 100% agreement, but let's see what we get. Okay, so we sent something which has a very high chance of being in upstate, but not very high in downstate, and we got similar looking. And if you measure that how much it got, it's a 99.3% match, which is pretty impressive. Okay, and this is typically the case. Even in a quantum computer, you will get 99% agreement even with the current hardwares quite easily. Okay, so we are almost done. This is the final experiment, I promise. And the good thing is that I'm not even going to explain how this works. So hopefully this would be interesting enough without the explanation. So let me explain what is the game. It's a game of guessing. So for our last experiment, we will play a game. And this game is that I have a secret number, which you have to guess. Guessing is not the point. The point is, how many guesses or how many questions do you need to take before you reach the correct answer? That's the point. So I will tell you some information. I will tell you how many digits of the secret number I have thought. Okay, 7 digit, 10 digit, whatever it is. And you are allowed to ask me questions like, is the third digit 5? Or is the second digit 7? Questions like this, to which I will answer absolutely truthfully, yes or no. Okay. The success of your performance lies on how few questions you need to ask. So if there are 2 players, somebody guesses that same number in 7 guesses, somebody guesses in 12 guesses, the 7 guesses player wins. Okay, that's the game. Is the setup clear to everyone? Okay. Before we move on to quantum computers, it's a good idea to sort of pause a bit and think that how to best play this game if we did not know quantum mechanics. If we did not know quantum mechanics, what is the most efficient strategy that you can run if you are, if you want to run it on a classical computer? How should we play this game? It turns out the best or the most efficient way to play this is not in decimal or any other number systems, but in the binary number systems. So just for, I'm sure most of you know what is binary number, but just for case somebody doesn't know, the familiar decimal system works like this. That suppose I have a number 3927. What do we mean by this sequence? We mean that the 7 multiplied by 1, 2 multiplies by 10, 9 multiplies by 100, 3 multiplies by 1000, and that's the total number, right? That's the sum. That's how it works. For a binary number, we express everything using only 2 digits, 0 and 1. So how does that work? So suppose I have a sequence like 1, 1, 0, 1, 0. This subscript 2 reminds us that this is a binary. This is not 11,010 in decimal, right? So if we do the same thing, but except for powers of 10, now it's powers of 2. So 0 should be multiplied by powers of 2 to the power 0, 1 should be 2 to the power 1, and so on and so forth. And if you just do the normal addition, this is nothing but the number 26 in our decimal system. Okay? So we can convert everything into any decimal number, we can convert it into binary things. Now the first counterintuitive thing you should observe is that I'm saying that going into binary is more efficient, but going into binary always increases the length of the number. You have something which is 2 digit in decimal, you have something 5 digit in binary. So why is it more efficient? Anyone wants to have a guess?
Because I immediately know the answer. If I ask, is it
Exactly.
a 1? And you say, no, I know it was.
Exactly. So it's because of that, and there is one more advantage. If I tell you in binary, so suppose I have this thing. So suppose I say that we are playing in decimal and it's 26. On average, you will take 5 guesses to fix the number 2. On average, you will take 5 guesses to fix the number 6. So on average, you will take 10 guesses to fix the number 26. It's a 5-digit binary number. And if I say that I have a 5-digit binary number, you immediately know that the leftmost digit is 1. If it was 0, it wasn't a 5-digit number. It was a 4-digit number. So that has increased 1. And for the rest, as you pointed out, you have to ask 4 questions. Ask whatever you want. Is the second digit 1? If I say yes, you know the answer. If I say no, you also know the answer. So you just need to ask one question per number of digits. So essentially for an n digit binary number, you need n minus 1 guesses, and this advantage always wins over the fact whatever disadvantage you get by increasing the length of the number. So that's the essential thing. Now the whole point is that, so we have figured out that if we have a 10 digit number, I will need 9 guesses. If I have a 100 digit number, I'll have 99 guesses, so on and so forth. The whole question is that how many guesses do you think the best program in a quantum computer will take? So if anyone knows the answer, please opt out from the polling. Let's have a poll. So suppose I have a 10 digit number. The classical computer will need, say, 11 digits. So classical computer will take 10 guesses. How many do you think the quantum computer will take? So less than 10 or more than 10? How many thinks it's more than 10? Okay, nobody. Good. People are listening. How many thinks it's like less than 5, let's say? Okay. Well, most of you. Does anyone think it's between 5 to 10? Okay, there's 1. Okay, so now let's increase the number of guesses. Let's say I have, let's pick something exorbitant, 10,001 digit number. So I will need 10,000 guesses in the classical computer. How many think that it will be less than 1,000 for quantum computers? How many think it will be less than 100 for a quantum computer? How many think it will be less than 10 for a quantum computer? Okay, a few. How many thinks it will be less than 5? Okay, even fewer. Okay, so we have some guesses. So one last guess maybe, let's say you have 10 to the power 10 lengths. How many people think that it will be less than 10,000 this time? 10 cube, a few. How many people think it will be less than 100, let's say? Okay, there are more somehow. I don't know how that is logically possible, but okay, so we have some things. So does anyone want to take a guess that what sort of ballpark number we have? Or we want to go to the, so while we run the code, maybe. Okay, so this thing is called quantum oracle. And the most efficient algorithm in quantum computer that does this thing is called Bernstein-Vazirani algorithm, named after the two gentlemen who came up with this. And we know how this works, so we can just simply start. So let's initiate the system. We have to give a number. So you can you see this thing here? That's the maximum limit the program can take. That's not the limitation of quantum mechanics, that's the limitation of my laptop. So don't judge it too harshly. So we can have something like, let's say, 8-digit number. So yeah, please go on, 8 digits. Someone, please. You can give it in decimal. The computer will convert it to binary. So someone give me a digit. 20, okay, 20 million I cannot time. Just one digit at a time, please. Give me a digit. 2. 7. Someone from here? 6. 4. 2. 0. How many are there? 2 more, 1 more maybe. 9. Okay. So 2764209. One final chance. How many people think? What are the number of guesses? How many people think it will be less than 1,000? Okay. How many people think it will be less than 100? Okay. How many people are willing to bet 1 million crown that it will be less than 10? Okay, somehow when you put a wager, things becomes a bit tricky, right? Okay, nobody wants to bet that it will be less than 10, but many people thought it would be less than 100. So, you have classical queries that you would require is 21. The number of shots that the quantum computer required was just 1. And now the point is that it does not matter how long a string you give. It will always require only 1. And the way this works is that the quantum computer is capable of putting all the digits of these binaries into a simultaneous superposition and ask this question, are you 0, are you 1, are you 2, simultaneously on all of them. And using exactly the same maths that I told you, but much more longer and tedious derivation, you can actually prove this, that this is something that will happen no matter how long a string you give. It will always take only one shot to guess the answer. So that's like a order, what we call an order n improvement over the computation time. Okay? So that's it. So with this, let me move on to the takeaways. The universe loves both and, not either or. So don't fear superposition. You see a weird vector in an abstract space in a superposition state, don't be scared of it, embrace it. Entanglement is inevitable. It is in fact part of the reason why we seem to be classical. This is something that I did not explain today, but maybe we can explain it for the 101st years of quantum mechanics. And we all are powerful observers, right? You can freeze a quantum state just by watching it. So use your power wisely. Which quantum state you want to freeze at what? And quantum computers isn't magic. It's just much cooler math. And we are finally learning how to make hardwares that speak that language. And quantum mechanics is here to stay. We have many, many more things to know, but we also have discovered a lot of new things. And I so hope that people who are seeing this for the first time at least, that your journey into this fascinating realm is starting. And if you want to know more, I can give you one concrete evidence that how you know that high school students can learn this thing. Because in 2022, in part of this Otevzhena Vieda program of Czech Academy of Sciences, I had 3 high school students who worked with me for 1 year on quantum computers. And I'm very proud to say that they won the first prize that year with their project. And we created a set of notes targeted towards high school students, which is available. If you scan this QR link, you feel free to take a picture. And you can go there and find more details if you want. And you can always write to me. And finally, thank you very much for coming here.
So, do we have some more questions?
Yeah.
I do have one, but it's related with physics, but you're jumping out into the field of neuroscience. And I have this theory. So you have year power 1, year number 0, and when you see the connections, it's automatic, immediate. So as you mentioned, the quantum mechanics is basically in nature, right? And with everything is spontaneous. I don't know if you're interested in this file, if you're knowledgeable, but do you believe that brain also works behind or under the quantum mechanics rules?
Okay.
I don't know if you understand my question.
I understand your question.
Peripheral relates that the brain actually works with similar rules.
I understand your question. So there are 2 layers of answers to you. First is that, as I said, everything is quantum and brain is part of everything. So in that sense it is. But you are probably asking that at the level of brain functioning, the functionality that you're observing in some imaging data or some other electrical activity, whether that really requires quantum mechanical rules to be described, or can they be described by something that is classical? I'm not an expert on this, but to the best of my knowledge, I don't think that there is enough data in any of the imaging or any of the things that has been collected by the neurologists to suggest that you really need quantum rules to explain the neural connectivity of any kind. People have postulated this idea before, and it has always been turned out to be not necessary. But who knows? I mean, I'm not leaving out the possibility.
I was just curious, there are like lots of theories with this.
Yeah. Yes.
In the last experiment where the quantum system of the computer simultaneously asks each digit at the same time so that the whole thing is just one shot. But this isn't the case. It's asking another quantum system, right? If it's asking a classical system, the classical system will take one time to answer each. So in that case, it's not just one doing, is it? It's between quantum systems.
Okay, so that's a good point. So the part of the quantum algorithm is that this secret number is stored in what we call the quantum register. It's a memory which is capable of storing a quantum data. So you can encode any classical information as a quantum data as well. Suppose you give me the number 0, the bit 0. I can just simply say that, okay, this is precisely the state 0. And I can map the bit 1 as precisely the state 1. So I can always take a classical data and store it in a quantum register. And this question is asked at the quantum register itself, and therefore it takes one shot. But if I did not store it in a quantum register, then of course, I mean, a quantum computer will not even act on classical bits. It acts on quantum bits. Yep. Yes, please.
Now it is a postulate that we cannot measure the state vector, right? But can you imagine a super cool technology which enables us to measure state vector directly?
I'm pretty sure something like that is not going to happen.
Never ever.
Never ever. Well, okay, let's not say never ever. But I will also point out to you that there are physicists who will say otherwise, who will say that it is possible that you can have some meaning to the state vector one day. And there are some people who are actively trying to think along this. For me, my point is that you do not need to know what the state vector is really doing or etc. We can use the state vector in this way and we can predict outcomes of experiments to great precision. I should tell that quantum mechanics is the most precisely tested theory, not just in physics, but in all human science. So the most precise prediction of quantum mechanics has been verified to 12 decimal places, which is absolutely insane if you compare to the other sciences. So I'm happy, but some people are not. But I'm in part of the majority. So any other question? Yeah, go on.
That continue at this point. I think that's the thing that touches the postulates of quantum mechanics. So
Yes.
when we formulate or somehow experimental prove that the wave function is some real object, measurable, what would be the implications for the quantum field theory or other higher theories? Would it destroy them somehow?
Well, it depends really on what is the modification. So somebody has to first come up with some modification, and then
Implication of the wave function, the state vectorism.
yeah. So for example, I can tell you that there was one modification that was proposed way back in 1950s by the physicist David Bohm. And he said that, there is something more to it, which he called a pilot wave. And it turns out that when you have that system, you can write down a version of quantum mechanics, but it really does not play well with relativity. So it doesn't work for quantum field theory, for example. So, but then it's a kind of a negative question. So it's very hard to rule out. What we can do at best is that if somebody comes up with a formulation, I can then say that, okay, fine, can you explain this with this? Yeah, but I mean, it's a pretty strong constant. So, which is why it's very hard to modify rules of quantum mechanics.
So the Bohmian mechanics is inconsistent with the relativity?
Once again, it's very hard to prove something is inconsistent, but nobody has managed to make it consistent after 70 years. So,
More questions? Okay, if not, then let's thank the speaker again.